In the previous part of the lecture, we talked about how you can perform static analysis on the paper to see whether your design for either the precondition or the postcondition is actually appropriate. Let me recap very quickly and then talk about the extended discussion we're going to have about the runtime rather than static time. So let's now talk about the two examples we discussed. In this case over here, for the precondition over here, the rule says that alpha should really imply gamma, right? However, it turns out this is invalid for this particular example because it's the other way around. Rather than alpha implies gamma, it's actually gamma implies alpha, right? And then to visualize it, you can see the gamma is exactly over here. That's a child class precondition. And then some value over here, let's say 12% for the battery level that satisfy the parent class precondition would not be satisfying the child class precondition anymore. So that's the invalid case, right? So that's about the precondition example we spoke about. What about the postcondition? The rule says that it should be the case that beta should really applies. Sorry about that. The rule says that delta should really imply beta, right? The postcondition in the child class must be stronger. You should ensure more than the postcondition in the parent class. So it is not the case that delta actually implies beta. It's actually the opposite. That's why we say it's invalid from the example. Specifically, you can think about the this is the precondition. So this is a postcondition for the child class, which is delta over here, right? So in that case, if the implementation only try to satisfy this particular postcondition by returning tomorrow events only, in that case, you are not going to actually satisfy what's guaranteed by the beta, which is over here, happens today, right? So that's kind of the discussion we spoke about. Okay, so these are the two invalid cases that we spoke about from the previous part of the lecture, and what we did was really about just proving something on the paper. So that's why I called it static analysis. So what we want to do now is to think about at the runtime, how are the contracts, especially when we have inheritance relation, how are they checked by the IFO runtime, right? That's something we'd like to talk about. So exactly how they check about the contracts really has some logical foundation that you will need to understand. Let's now go over some slides, and I'll go back to those two examples which I talked about to see, given that statically they don't really they are not really valid, but at the runtime, how are they going to be checked anyway, right? So notice that even if you find that a particular pre or post condition is poorly designed, it's not going to generate any compilation error. No, it's not. So that's kind of the analysis you have to perform, like a higher order analysis you have to perform as a designer. So otherwise you're going to get some weird behavior at the runtime, so which I'll talk about. So contract redecoration rule. So in the context of a child class, how are we going to add extra pre and post condition? So syntactically, in the context of a descendant class, for the precondition, we're going to say require else if we want to introduce more precondition. And in the case of postcondition in the child class, we're going to say ensure then. So now here, syntactically, the else and also the then, in the case of inheritance, will be required. If you simply, in the child class, you simply say require, and also you simply say ensure without the else and also then, it's going to be a syntactic error by the compiler. I will give you some intuition about why we're using an extra keyword for else and also an extra keyword for then. You will see that very obviously for the rest of the slides. You will see that. Okay, let's talk about, okay, so now we talk about runtime assertion checks, right? So now we talk about how exactly we evaluate the preconditions from both the child class and also the parent class that whatever precondition it inherits. Precondition first. Think about the original precondition is actually declared in the parent class. And then in the child class, we redeclare some extra new precondition. Okay, so now the way we evaluate if the dynamic binding, the instance is actually the child class, right? Let's say that the dynamic binding, that means we're going to invoke the precondition. Not only that we're going to invoke the new pre, but also we're going to invoke the original precondition. And the way we combine them together is by using or else. So why have we chosen such logical operator? Well, apparently if you want to combine two Boolean conditions together, you have to choose an appropriate logical operator. So now why in this case for the precondition, we're going to choose disjunction. The easiest way to understand is like this. As long as the original precondition is actually satisfied, In that case, the whole disjunction would just be true. Remember, the or else is like a vertical bar in Java with a short circuit effects, meaning that as long as this part here is already true, it doesn't quite matter what this will evaluate into. Maybe true, maybe false, doesn't matter. As long as the left-hand side is actually true, the whole thing will be true. So now let's think about why this logical property will actually make sense to what we talked about previously for the static analysis. So that means clients able to satisfy the original precondition, meaning that the left-hand side is actually true, they will not be shocked, right? So I'll get to the example in just a moment, but you can also think about why this will apply to our previous example. Okay, so as long as you satisfy the precondition from the parent class, in that case, the whole thing is going to be simply just true because of disjunction. And then, so if you want to see logical property here, so if you got the left-hand side is already true for the parent's precondition, it doesn't matter what this is. In overall, it's simply just going to be satisfying the precondition overall. Okay, and a precondition violation will not occur as long as the clients are able to satisfy what is required from the ancestor classes. Specifically, this is what's required by the ancestor classes. Let's see one example. Let's go back to this smartphone example over here. So now we know that statically speaking, this particular design over here is simply not appropriate, but there will not be negative. There will not be any compilation error. Let's see what's going to happen at the runtime. At the runtime, what's going to happen is we're going to put these two predicates together using disjunction. So what's going to happen is this one alpha over here and also gamma over here. We're going to check alpha disjoint with gamma over here, right? So now think about what's going to happen over here. I can tell you that in short, it will be as if this particular stronger precondition was not even declared in the first place, because we know that gamma is actually stronger than alpha. So when you disjoin them together, it will be simply just equivalent to alpha. But how do you see that? It's very easy to see when you see the diagram. So now you can see alpha is basically the satisfying set over here. When you say disjunction, it's like a union. If you want a union with this particular gamma, which is stronger, the overall predicate will just have this particular satisfying set, which is the union. So now overall it's going to be like this. So this will be the new, this will be the actual precondition that's going to be checked at the runtime. Okay, so this will be the one. Okay, let me just call it that just to make sure you understand. So now what's going to happen is, if you think about a 12%, so if you want to evaluate the 12%, the 12% is going to satisfy the alpha, so this will be true. Okay. However, the 12% is going to violate this part over here, the gamma. So this part will be false. But since it's a disjunction, so overall it will still be simply just true. Okay, so that means even though the design is actually poor, in which case the designer should really fix it. But just in the worst case, if the designer simply didn't fix it at the runtime, the IFO compiler will make sure, based on the logical foundation we just spoke about, is going to check their disjunction. In that case, we're still just going to check for alpha. In that case, the precondition will not be violated if you try 12%. All right, so I hope that makes sense to you. Let me just recap very quickly. Well, the discussion we had in the previous part of the lecture, we talked about, since this is the case, so statically we know that it's a poor design, so you should really fix it. But now we talk about another orthogonal issue. What about at a runtime? How does the IFO compiler or IFO runtime check this? So based on the logical foundation that we spoke about, what they will do is going to say, is simply just going to check the disjunction for both, just in case. In the case where the child precondition is actually stronger, in that case, it wouldn't really cause any violation at the runtime. What it's going to do is it will be absorbed somehow by the weaker parent's precondition. In that case, you will simply just check the union. In that case, this particular value will still satisfy the precondition for the parents. Right, so that's about a precondition. Okay, think about this example here. You want to think about two orthogonal issues over here. One is about static analysis. The other one is about runtime checks. So they are different issues over here. So let me go back there, and then that's about the precondition. Let's talk about the postcondition. The postcondition is going to follow in a similar way. So now we're going to use conjunction, but why? Let's think about this. So let's say the post condition that's really in the parent class is called original post condition. And in the child class, we got another additional new post condition. At the runtime, let's say the dynamic binding is in effect. Let's say the child instance is the dynamic type. In that case, we're going to check the conjunction of these two Boolean, these two predicates. But why? The easiest way to understand is, well, remember what we said before. As long as the parent's precondition is satisfied, the whole thing is satisfied, right? So now think about it this way. As long as the parent's postcondition, whatever that's really promised by the parents, is not satisfied, meaning that this part here is true, that means the whole thing over here should be considered as a violation. Okay. So now think about how this applies to the example that we spoke about, and then I'll get there. Okay. So let's read a little bit more. So failing to gain the original postcondition, which is inherited from the parents, will be reported as an issue, like a postcondition violation at the runtime. So if this is simply just false, you can see that from the logical property, if you got false conjunction, and then whatever the child postcondition is, doesn't matter, as long as the parent one is actually false. Overall, it's going to be false for the child instance. So let's read it here. A postcondition violation occurs will be as expected. So now this postcondition is actually as expected. If the clients do not receive at least those benefits that's promised from the ancestor classes. Let's see how this can be applied to our previous example over here. Okay, so now remember in the previous example we say that if there is such a implementation, remember the implementation that we spoke about, the orange one. Let me just call it that again. You can think about the orange part over here. Let's say this is the value that's really returned by the faulty implementation, right? You can think about this one here. This is the implementation that returns the tomorrow events only. So this implementation can satisfy the delta, but it cannot satisfy the beta, right? Because it satisfies delta because it always returns just tomorrow, and then it does not satisfy beta over here because it's not today. All right. So now at the runtime, what's going to happen? At the runtime, what's going to happen is it's going to conjoin these two post conditions together. So we got beta over here. So it's going to be beta conjoined with the delta over here. So now let's think about what's going to happen here. Let's say for this particular post condition over here, for this particular implementation, as I just explained, is it going to satisfy whatever that's inherited from the parent class? Well, apparently not, because it's always returning tomorrow events only. But whereas what's really promised by the parent class is today events only. So this part here is for sure going to be false. So now, even if this particular implementation is going to satisfy the child class postcondition, which means this will be true, doesn't really matter because the left-hand side here for the conjunction is already false. So that means it's simply just going to be false over here. Right? So you can see for this particular evaluation, it's simply just going to be false. So now let's think a little bit more generally. So since in this case, we have beta, let me just use a different color. Since we know beta implies actually delta, right? So now when we do, let's say beta, let me use a slightly different color here so you don't really get confused about the color here. So let's say over here. So now when you say beta and delta in general, if we know beta is already logically stronger than delta, so when we say beta conjoined with delta, it was simply equivalent to beta, right? Remember what I said previously for the precondition. What's really ended up being checked is actually the union. So what we're doing here is we are really end up checking the intersection. So what's really happening over here, you can think about it simply beta. So this is like the intersection of the two satisfying sets. So at the runtime, what really end up being checked really is we are only checking the beta, basically. So now if beta is already violated, so now you're going to get false, meaning that we're going to get post-condition violation. So let me write it down over here. So false simply over here means post-condition violation. Post-condition violation. And now let me emphasize that this is expected, because the implementation that we are talking about over here returns tomorrow events only, and it does not really keep the promise that's made by the parent class. So of course there should be some post-condition violation expected. All right. Okay, so that's about the discussion for the post condition over here. So please make sure you really compare these two examples over here about the precondition versus the post condition over here, right? Okay. Again, there are two orthogonal things we are checking over here. One is about static analysis by proving the implication, and the other one is at a runtime how the two preconditions or how the two postconditions are combined together using either disjunction or conjunction to check at runtime. So these are two different issues. Okay, so now let me go back here, and then so that's about the contract redecoration rules. So let's now consider some special cases. For cases number 1 and 2, we are thinking about what if the preconditions are simply missing from the parent class. Let's see example. Let's say for the precondition. Let's say we have the class called foo, and then it has no precondition. And then we have another subclass called bar, and it simply inherits from foo, and then redefine the f, right? So now we say require else new pre over here. Okay, let's now switch to iPad and think about what's happening over here. First of all, I want to emphasize, so we are assuming the following inheritance hierarchy. So we got a foo over here, and also we got the bar over here. More specifically, we want to say there is no the foo is actually not an intermediate class in the inheritance hierarchy, which means there should not be another class over here, maybe called maybe foo number 2. It's not the case, okay? So now we're assuming that it's not the case, right? That's not what we're considering. So now the foo over here is simply just the top of the hierarchy, just to make our special case simpler, okay? Top of the hierarchy. Okay, and then we got f over here, and also we got f++. So that's this architecture that we are speaking about. Okay, so when you're talking about this, so we actually spoke about this earlier in the course when we talk about precondition and postcondition. In a particular class, when you start with over here, if you simply don't have any precondition, it will be as if, okay, that you say require simply just true. It's simply just true. Meaning that from this particular class point of view, any input value is going to be okay when you actually try to invoke f. So now let's talk about what the consequence would be. So now the consequence would be, so now when you combine this particular true value here together with the precondition, right? We know that from the contract redecoration rule. So it's going to be true and then disjoint with the new precondition. So now what's going to be the outcome? Well, it will simply be, because this is weaker, so it simply union will just be the true. Okay, so this will be what's going to be checked at the runtime. So if the dynamic instance happens to be bar, in that case, even though it got something that's strictly stronger than true, it doesn't matter. It will be absorbed by this weakest predicate over here. So at the runtime, we'll only check for true. So at the runtime, even if the dynamic type is bar over here, only check this particular precondition, only check true for the precondition. Okay, so that's the first special case to talk about. Okay, so that's exactly what you will see on the slide. So that's exactly what I meant. Okay. Okay, what about the second special case? Let's say the second special case is where we still got a foo and bar, and we still assume the following this particular inheritance hierarchy, meaning that the foo is basically just the top of the inheritance hierarchy. It's not an intermediate class. Okay, so now we got foo and bar over here. And now when we don't have any postcondition, it will be as if, also as we said before, so that will be as if there's no constraint whatsoever on the supplier. So now it would be as if when we say ensure over here, and then simply true. So this means any output value supplied by the supplier will be okay. So now think about what we're doing here. We're basically giving something that's actually stronger, because any predicates will be stronger than the true. True is the weakest one. So now what's going to happen at the runtime? So now at the runtime, what's going to happen is we're going to get true over here conjoined with the new post. So we are saying that what we said before, if the postcondition for the parent class is not satisfied, we should have a postcondition violation. That's what we said before. But now it's not possible to dissatisfy this particular true predicate. It's always satisfied. So now this will just be simplified into like a taking the intersection of the two sets. So now it's simply just going to be the new postcondition. So this will be what's going to be checked at the runtime. Okay. Okay. So now just want to okay, let's just say this: when the dynamic type is the bar, check the new postcondition. The new postcondition for the postcondition, new post for postcondition. Okay, so now hopefully these two special cases where the contracts for either precondition or postcondition is missing from the parent's routine is clear to you. Okay, let's now go on to talk about another two more interesting test special cases. Okay, let me now go on to, okay, that's exactly what I just explained. So now what about the third case? Let's say we got the precondition not missing from the parent class. However, we got missing precondition from the child class. So now what's going to happen over here? Okay. To really guide you through the answer, so let me just go here. Okay. So now for this one here, I would suggest we think backwards. Okay. So now think about what's going to happen here. So we know that this is basically the parent's precondition, and now we want to know it will be as if what? So require else. Apparently it's not really declared. We want to know it will be as if declaring what. So now let me just say question mark over here. At the runtime, what we're going to do is we're going to say original pre disjoint, right? It's going to be disjunction for the precondition. So whatever the question mark is, we're going to figure out what the question mark should be. Okay. So now what should this be equivalent to? So now intuitively what's going to happen is, since we already declare the precondition over here in the parent class, and when in the subclass is simply just missing, so that means what we should do really is to simply inherit the precondition from the parents verbatim, and then let it be checked against the child descendant class dynamic objects. So what we really want to put as the equivalence result over here should be just the original pre. Okay, so now given that we know about the two sides of the equation, and we are just missing, we know that the two sides should contain original pre, and the result should be also original pre. So now given the disjunction, and also here, think about disjunction is like a union of the corresponding satisfying value sets. So now what should this be? Well, for any set, given set, union with empty set should be equivalent to itself, right? So that's kind of the intuition you can have. So now what we should get is, what's the predicate that has the corresponding satisfying value set being empty? Well, false. Okay, so this should be false over here. So that means it's as if we declare false over here. Okay. So one more thing to really mention. So we are basically saying the following. When you actually don't declare anything over here, if the precondition for the child class is simply missing, it will be as if the child class is doing something that's meaningless, meaning that they simply strengthen the precondition into the strongest possible from the original precondition, in which case the runtime is simply just going to make sure once you do the disjunction, it will just be equivalent to the original precondition. So that's what's happening over here. So this typically is the common the case that requires a little bit more intuition and more thinking into it. Okay. Okay, let's now go back to the slides. So this particular case is about as if require else false. Final case we would like to talk about is, what if the postcondition in the child class is actually missing? So this one here, we're going to follow the similar reasoning process. Okay, let's do that quickly. So now what we have is, we actually got the original postcondition from the parent class, and then it's simply nothing over here. So we want to know, it would be as if, when we say ensure then what? That's something we would like to figure out. Okay. So now let's now try to do the backward reasoning as we did in the previous one. So what we have is, we got original post And also we got the question mark over here, so we got these two. How are they combined together at runtime? As we learned, it's going to be conjunction. And now, intuitively, if we actually got postcondition specified for the parents, but the child class is simply missing, in that case, we simply want to inherit verbatim the postcondition so that it can be checked against the dynamic objects of type the child class. Okay? So now the result for the equivalence should be original post. So now we know about the two sides of the equation, and we know what's really missing. So now, so think about this like doing an intersection. So now we want to make sure whatever intersecting with for the original satisfying value set should be equivalent to itself. Well, it should really conjoin with not really false, right? Because false would just give you empty set. In that case, this would not be original post anymore. So what you should really do is the universal set. And what predicate give you the satisfying value set being the universal set? True. So this will simply just be true. So it will be as if we say ensure then true. Okay, so you can see true and whatever is going to be whatever. Right, that's the axiom that you learned from 1090. So let's go back to the slides. You can see now, so it will be as if we say ensure then true. So you can think about the special cases number 3 and number 4, the way we figure out exactly what should be the missing part for the pre and post condition. Think about it in the backward manner as I illustrated to you. But for the first two cases, it will simply just be, the missing will just be true for the precondition and post condition. Alright, so that's about the 4 special cases I would like to mention to you. Before I make a concluding remark for this lecture here, I would like to speak about one more subject about class invariants. So every class inherits invariants from all its ancestor classes. Not surprising because we also inherit all the pre and post conditions from our ancestor classes. So now, since the invariants are like post conditions for every routine, so the way we actually accumulate and also check the invariant at the runtime in the context of inheritance will be very similar to postcondition. So let's see one example to confirm. Okay, so now, we got one class over here called polygon with an invariant. So we simply got vertices, which will be just an array of points. So for polygon, by definition, there should be at least 3 points for the polygon. The smallest one will be triangle. So that will be the first class. Let's say we got one class, descending class called rectangle of polygon, and then we simply got invariants vertices that count equals 4. So what do we have right now? So think about what's happening over here. So we have one class as a parent class over here called polygon. And then let me just draw that properly. So we got polygon. Let's say that's effective. And it has the invariants over here. Let me just omit the declaration for vertices. So it's going to be vertices dot count actually larger than or equal to 3, at least a triangle. And we have an inheritance relation over here. So the subclass that we're talking about is the rectangle. Okay, let me just draw that over here. So this will be just another class over here, rectangle. Okay, let's say that's also effective. And we have a different invariants. You can think about some extra invariants, like an extra post condition for every routine in the rectangle. And this will be vertices dot count is exactly equal to 4. Okay, so now let's go back to the slides. So that's basically what we have so far based on the slides. So now what will be checked at the runtime on the rectangle instance? Let's say the dynamic type is actually rectangle, so what will be checked for the invariants? So what's going to happen is, since we know they're going to be accumulated together, so this invariant over here is going to be combined with this invariant over here. So you're going to do a little bit of logical logical calculation over here. So it's going to be, think about vertices that count is simply, let me just say C, just for short. C larger than or equal to 3, so that will be the invariant at this level here. What about the invariants at this level here? It will be conjoined together with C exactly equal to 4, right? That should be equivalent to what? Exactly just 1. You can think about this predicate here is strictly stronger than this one over here. So having conjunction is like having an intersection. So it will be the smallest set. So it will be C is equal to 4. So what really ended up being checked will be just this invariant over here once we do the math. Okay, so now that's about exactly what I just said. So now let's have one question for you. Can pentagon be a descendant class of rectangle? Think about this is more like a design choice. If you want to create a new class called pentagon, you're not too sure whether you should really put the pentagon as a subclass of rectangle. So now I want to make a design decision together with you based on invariance declarations. Let's go back here. Let's think about it. So what we want to do is we want to introduce a new class over here. Let's say if we really wanted to add a new subclass of rectangle. So what's going to happen is, first of all, we're going to have the inheritance relation, and then we're going to have our new class over here. Let's call this new class over here pentagon. So pentagon. Let's say that's also effective. And now, if we follow a similar logic over here, what should be the appropriate invariance for pentagon? Well, by definition, the vertices that count should be equal to 5. So invariance. Okay, invariance is going to be vertices dot count is equal to 5. So now the question is, what's going to be checked for the invariance if the dynamic type is actually pentagon? So we're going to do a similar calculation over here. So now again, let me do the use abbreviation. Vertices that count is simply just C. So let me just do a slightly different conjunction here. So C larger than or equal to 3. So that's from one of the ancestor class, the invariant from there. And also the parent class, which would be C is equal to 4. And then the current class, which is C is equal to 5. So now what should that be? Well, even though we know that this is simply just equivalent to C equal to 4. But now when you say C equal to 4 and C equal to 5, can both be satisfied at the same time? Apparently not. So this one should be false. So now the invariance at the runtime that's going to be checked on this pentagon, if we put it as a subclass of rectangle, is going to have the following disastrous consequence, meaning that you're just going to have class invariance right in the beginning and always. So this is not a good. So what's the conclusion from this? So the conclusion is pentagon should not be a subclass of rectangle over here. Rectangle. Okay, so hopefully you can see the reasoning process over here. So in the context of inheritance, there's some special case you want to talk about, like an invariance, which is just like a postcondition for every routine. Okay. Okay, so that's about this particular last point, last example. Let me now make a conclusion about what we have done, we have covered in this lecture here. In general, given any two classes which is connected by inheritance, let's say in the parent class we simply got original precondition, original postcondition, and in the child class we simply declare new precondition and also new postcondition, right? We're using require else and also ensure then. So the else part really indicates we're using disjunction at the runtime. And then over here it's like and then. So it's like indicating we're doing conjunction for the postcondition at the runtime. So now statically in the design time, so this is something you will have to prove or justify manually as a designer. So this is not going to be something that compiler will check for you. So proving if some predicate is a tautology is an undecidable problem. So it cannot be done by the compiler. So you have to prove it manually by your hands. So we said about these two rules. For the precondition, the new precondition should be weaker. So that means we're requiring less. And also the new postcondition must be stronger, meaning that we are ensuring more. So for each of these implications, you have to either prove it as a tautology or you have to disprove it by providing counterexample as we shown in the previous example. And then for dynamically at the runtime, you will have to make sure whenever you check the precondition, you have to disjoin the two preconditions together. And then whenever you want to check the postcondition, you have to conjoin the postcondition together, including the invariant as well. So basically, for the runtime, you have to think about dynamic binding. So exactly what a dynamic type is for the context objects is going to determine exactly what the new precondition is going to be used for the disjunction. So that's something we also spoke about in the previous example. Okay, so that's about the two important aspects which are orthogonal, which you have to study separately, but they're also somehow connected. So that's about this lecture here. Before we move on to the next design pattern, in which case we're going to show you some subcontracting simple application, but make sure you study the subjects over here thoroughly before you move on.